Okay, hello everyone. It's my great pleasure to be here today to deliver this tutorial. So first of all, I would like to say thanks for the kind invitation from the conference committee, especially from Catherine and Professor Yang. So thanks for giving me this opportunity today to share some of my story and also my understanding of medical robotics. So today, I'm going to talk about medical robotics. I think this is really going to be a fast-growing field. For those of people who are working on robotics, automation, mechanical engineering, probably today's tutorial will be very fundamental for you. But I'm actually putting quite a lot of research examples from my side, also from some of the other groups. So I hope that bit will be interesting for you. For those of the people who are not specifically working on medical robotics, for example, if you are working on medical imaging, medical informatics, I'm quite certain that in the following couple of years, you will have much more opportunity to work together with a robot because this is really a fast-growing field. So I would hope that this tutorial will give you some kind of very fundamental understanding of medical robotics, and you know what are the type of things that you need to consider if you are going to work with a robot. And I know there are lots of postgraduate students in China, from China side, who is listening to this tutorial. So I hope this will be a good opportunity for you to learn some of the things from me. And also, I think if we have a clinician with us, probably again in the next couple of years, I guess many of you may have the chance to have one or two robots in your hospital. And then it's really a question to ask, when you work with a medical robot, what is the type of things you need to consider? If you're going to buy a robot, what is the question that you want to ask? So I hope this tutorial can answer some of these questions. So my name is Shuangyi. As Catherine already introduced, I'm working in Chinese Academy of Sciences Institute of Automation. And before I joined my current institute, I've been studying and working in King's College London for many years. So our conference EU and China Summit. So probably I'm the right person to attend. Okay, so just at the very beginning of my presentation, I would like to give a very brief short introduction about myself and also about my research. So I used to work on medical robotics in King's College London at School of Biomedical Engineering and Imaging Sciences. And for most of the time, I stayed in St. Thomas Hospital, which is what this picture actually shows. So we had a really good scenario, which is sitting along the River Thames, opposite to the House of Parliament. On the other side is the London Eye. So St. Thomas Hospital is a really famous hospital, one of the earliest hospital in UK. If you like to watch UK drama like Downton Abbey, you will probably see this hospital actually appear in the very early days. It actually becomes very famous in before the World War I, during the Crimean War time because of the Nightingale. So at the time when I was in King's, I'm working on imaging analysis, surgical guidance, and also 3D printing. And specifically, I would say myself is a robot developer. So we managed to develop the world's first transesophageal ultrasound robot, transthoracic ultrasound robot, and also had a really interesting project on intelligent fetal ultrasound robot. So since from the end of the last year, I came back to my home country, China, and joined Chinese Academy of Sciences Institute of Automation, which is known as CASIA. So probably you guys are not that familiar with this institute, but we are one of the institutes that is very dedicated to AI and robotics. If you look at the field weighted citation impact in AI from Scopus last year, we rank at number 7 among those very top universities in the world, like MIT number 1, SAMU number 2, NTU from Singapore number 3. So in here, specifically for medical robotics, we are interested in a number of different subjects. For example, the catheter robot. So this one is one of the commercial ready product from us, which is a robot to deliver catheter into the coronary artery system. This is one of the very important projects that we have been working on for many years. And we also do rehabilitation.
Excuse me, Shuangyi. Actually, on the right side of the screen, there's a area is blocked.
Okay, can you see? Okay, I have moved
that to. Yeah, that's good. Thank you.
Okay, that's good. Okay, I will carry on. Okay, so we also work on rehabilitation robots. So this is another commercial ready product we developed. So in here we are really doing translational research from prototyping to make the system that can be eventually really go into the hospital. And since I returned, I also managed to set up a small new lab that is dedicated to diagnostic robots and also continue some of my work on ultrasound robots. So this is about myself and about my research. So for today's tutorial, I'm going to cover quite a lot of content, and we'll start from the research progress to give you a brief introduction of history of medical robotics and where we are at the moment. And then we're going to talk about robot configuration. Basically, if you have a robot in front of you, how could you describe this robot, and what are different type of categories that a medical robot can fall into, and you know, what are the representative work for those type of robots. And then we're going to talk about robot design. Assuming that if you're going to build a medical robot, or if you are a person who is going to work with a medical robot, what are the things that you need to consider? Or even if you are a clinician that your hospital buy a robot, and at the time when you see your provider, what is the question that you may want to ask, right? And then we're going to talk about force sensing and control, which are, I think, the very important research directions on medical robotics. But I'm going to cover some very fundamental concept of that, because today is still a tutorial. I think it's very important to show that basic principles, because probably our audience are from different background. We have many postgraduate students in China to listen to this presentation. So let me just introduce those sort of things. And then we'll also talk about pre-planning and navigation, which will be a very important domain that medical robot meets with medical imaging, which comes to the medical imaging computing and computer-assisted intervention. So we'll talk about how medical imaging is integrated into robotic system. And eventually we're going to talk about the safety, because safety, apparently this is going to be one of the most important consideration for medical robot compared with industrial robot. All right, so this is a brief syllabus of today's tutorial. We'll start with our first section, research progress. So, of course, normally when we have this type of tutorial, we will start with history. If we look at the history of medical robotics, we need to go back to 1980s. Where was the time? That was the time actually robot has been used in industrial. For example, the Puma 560. I'm going to talk about this robot again later on, but that was the time actually the robot started to be used in industrial. And immediately people think, why don't we try to use this robot medical applications? And then we have the arthrobot in 1983, which is for the bone mountable hip arthroplasty surgery. And we also had the Puma, which was used for robotic neurosurgical biopsy and also the laparoscopic surgery. That was at the time of 1980s. When it comes to 1990s, I think there's an important evolution in surgical technique, which was the presence of minimally invasive surgery and also the laparoscopic surgery. So that apparently changed the medical field and also had a great impact on medical robot design. And also, this is also the same period of time where the telepresence surgery becomes very popular. And I would say this was motivated by the space station and also the battlefield applications. So if you really see the history, there were lots of support from the organization like NASA at that period of time. So there was some representative work at that period of time. For example, the Probot from Imperial, which was used for prostate surgery. And it should be noticed, this is one of the earliest robots that used imaging guidance to assist robotic surgery. And we also have the ASOP from Computer Motion, which was the first FDA-approved endoscopic surgery device. And also we had a very famous robot called RobotDog. We're going to talk about this robot later on again, but this was the first robotic total hip arthroplasty robot, which is called THA procedure. And specifically, I think this was one of the first robots that used pre-operative planning in 3D and used that sort of thing to guide the robot to perform the procedure. that was the time in the 1990s. And when we come to 21st century, I think we came into an integration phase, which means we had instrument, camera, endoscopy, and also the navigation and imaging assistance, all these sort of things coming together. So the robot really become to something like a system, like system level integration. We had some of the representative work, for example, the ZEAS, which was one of the robots that first be used on the coronary artery bypass graft, which was a cardiac surgical procedure. So if you look at this robot, the ZEAS, it basically has two arms to replicate human motion, and these are the two arms to represent human motion, and it has the third arm for camera system. And we also had Da Vinci system, which apparently many of you have already heard about that. So for example, if we just have the opportunity to list one of the medical robots, then I think 99% of people will choose Da Vinci as the example, because this was the first fully integrated robotic surgical system approved by FDA. And this is widely used for minimally invasive surgery, multiple surgery. It has the integration of endoscopes, instrument, and cameras. And that was the very brief history. And what is the current stage? I think the first type of robot that are very widely used actually for the keyhole surgery, and also we can call them minimally invasive surgery, minimal access surgery, which has been widely used to replace open surgery. So when you perform this type of surgery, then you need to use this type of small endoscopic camera and also this small, this long, thin, rigid instrument, and you have multi-port for your surgical device and also your endoscope device to go into the patient body, and your surgeon will perform the procedure under the guidance of the camera imaging. So this is the basic concept of the minimally invasive surgery, and basically the Da Vinci system was built to do this type of surgery. And this shows the configuration of the Da Vinci system, which has an important concept in here called master-slave, where the surgeon will work at the console, what we call, this is a master, and the robot will be in close contact with the patient, we call them slave. So because of this configuration, our clinician, they don't need to really stand up, and then they can control multiple tools within these small areas. And because of the use of the robotic arm, they can reach higher position, and also you can get rid of some shaking movement, which are also one of the benefits of using this robot. And also, in addition to the surgical robot for minimally invasive surgery, there's also another very important category for the interventional procedure, which means we're going to make a small cut or hole to gain access to the inside of patient body. And this is widely used, especially I will give an example for cardio application. I'm just going to replay this because there's a video in here. It doesn't actually show. Okay. So this is an example from the COPAS. Okay, so the basic concept in here is basically for some of the interventional procedure, because you don't actually open the patient body, so you can't see the device. And because that, you need to use imaging guidance. So normally, when you use imaging guidance, you probably will use the X-ray C-arm, which will give you a real-time X-ray imaging, which will has really good contrast to show the device. And at the same time, for some of the procedure, you need to use ultrasound as well, because that will give you a really good contrast of the soft tissue, and you basically have a hybrid modality navigation. But the result of that is your operators, clinicians, sonographer, anesthetists, they are all exposed to X-ray radiation. And because of that, they need to wear heavy protection clothes, which are apparently uncomfortable and bulky. And many of the surgeons, they were suffer from the orthopedic injury. And because of that, we started to build this type of intraoperative interventional robot, which means that you can control them remotely in the console, and the robot is actually on site, so you don't need the surgeon to be on site. And if you think about the scenario, which means the operator could be in somewhere even more far away, for example, in another city, another country. In addition to the interventional robot, there's also newly trained on the NOTE robot, which is called natural orifice transluminal endoscopic surgery, and also the single port procedure. So we know we have open surgery, and which has been greatly replaced by the laparoscopic. And then we also have different type of flexible endoscopy device that can go into the patient body to take a camera imaging. And if you combine these two technical devices together, then you may end up in this NOTE device, which means it is a flexible endoscopic device, but has multiple channels within the device. For example, one channel for imaging and the other channels for surgery. And then the problem comes with that is for a manually controlled device, it might not be that intuitive. For example, you need to use your two hands to control. And some of the work was done to robotize the NOTE endoscope. For example, this was one of the work on the top right. You can see that they put some motors and actuators on the conventional NOTE endoscope. And as a result of that, they can now control with one hand. And the bottom picture shows one of the newly released product from Da Vinci, which is a single port robot. And you can see this picture very clearly. It has multiple channels within one entrance. So you have camera in here, have surgical devices in here, and you just need one port to access to the patient body. We also have a rehabilitation robot, which is also a very important research area in medical robotics. You can see some of the examples, for example, the Locomite from Switzerland, which is a exoskeleton robot to manipulate patient hip and knee. And we see the robot that can manipulate the patient foot for the picture B and C. In picture D, we see the robot to train for the training of a wrist and forearm. And for the E, we see the robot for the shoulder and elbow rehabilitation, and I for individual fingers. So you can see a different level of rehabilitation. And also we have another type of robot, which is mainly the area that I'm working on is endoscopic robot and also imaging robot. Probably ultrasound robot is one of the example of that. For example, gastroscopy device. It was a manually controlled device, and we had some problem with that. For example, you need also training to perform the procedure, and also you need two hands to do that. And some of the work will use robotic technology to make the kind of upgrade to the system. So you now become something that you can promote. You can control with one hand, or even you can control remotely. So the similar example is for this robotic renal endoscope device, where you can see that the surgeon can control the probe with the assistance of a kind of robotic holder, so they can control with one hand. The bottom left picture shows the example of the robotic transrectal ultrasound. So this is a very important kind of intraoperative ultrasound device, which was used to examine the prostate. And the problem with that is you need someone to manually hold the device for quite a long period of time, especially if this device is used to guide surgical procedure. And because of that, we can make a robot to do that. And we know one of the things that the robot is good at is just to hold something for a long period of time. And also, because of the use of a robot, it gives you a really accurate positioning, which means you can rotate the probe in a very high accuracy. And we know that this type of device, conventionally, it can take 2D ultrasound. And by rotating the probe 360, you may be able to reconstruct a 3D imaging of the prostate. And that is also the additional benefit for using the robot because it gives you a very accurate positioning. And we also have the robotic fetal ultrasound, which is a type of robot that is used to take ultrasound imaging. And the use of the robot enables our operator to control the robot remotely from somewhere else, which means our expert doesn't need to be on site. They can be in somewhere remotely to do the fetal screening. Okay. So now I'm finishing the first section, which was about a little bit about history, a little bit about the current stage. And then I'm going to talk about the configuration. So I'm going to cover some very basic concept of robotics. So for those of you who are just working in this domain, this might be very fundamental, but I hope this will be useful for some of our postgraduate students. Okay, so for example, if there's a robot just in front of you, how would you describe the robot? I think that the very fundamental elements are joints and links. And we can see the robot, basically, it is a linkage of rigid bodies that are connected by joint. And normally you will have two important types of joint. One is called revolute, which can generate rotational movement. And another type of a joint called prismatic. And usually we use the letter P or T to represent that, which can generate translational movement. And normally, it is very important to know that the order of links and joint will always be the joint goes first and then the links follow. So if you look at the picture on the right, you will see we have joint 1 and then it's the link 1. So by actuating joint 1, link 1 will rotate, right? Another very important concept in here is called end effector, which means the end structure that the robot holds. For example, a camera, an endoscopic camera, ultrasound probe, or a surgical tool. These are all the end tool that the robot holds. So once we know that we can describe a joint, a revolute joint or prismatic joint, then we can describe a robotic arm. For example, the Puma 560, we have already mentioned this robot at the very beginning. So Puma 560 was the first modern industrial robot, and you can see the configuration of this robot as RRRRR because it has 6 revolute joints. And we also have another Stanford arm in the early days, which has a prismatic joint. So you can see this long axis, which is a translational axis. So the configuration of this robot will be called RRP, RR robot. So rotation joint, and then a translation joint. So both arms were designed by one of our robotic pioneer, and they both now are in the, you can see that in the Smithsonian Museum of American History in Washington, DC. So if you have chance to go to that museum, do have a look at this robot. So when you have the tool to describe a robotic arm, then you can look into some of the combination of the joint. And normally, the first 3 joints of a robotic arm are generally responsible for positioning the robot, and will the rest of the joint take the responsibility to orient the tool. And then you have the configuration as PPP, 3 translational. For example, this is widely used for CNC machining, 3D printing, which we call them Cartesian or gantry robot, which means the configuration, the workspace of this robot is in Cartesian coordinate. And we also have the configuration of RRP, rotation joint, and then a prismatic joint. So their workspace is like a polar or spherical workspace. And we have cylinder robot, which has the configuration of RPP, so rotational joint, prismatic joint, and then prismatic joint. So normally this type of robot, they fit into tight space and usually work with the task that requires round symmetry. And then we have D. Picture D shows the horizontal articulated arm, which has the configuration of RR. So rotation joint, but they are all rotating in a horizontal plane. And there's a very important representative robot called SCARA robot. I'm going to mention this robot again shortly. And we also have the vertical articulated robot, which I think is the most widely used configuration because it resembles of a human arm. So this is our configuration, and you know this. You can notice these rotational joints, they are actually happening in a vertical plane. So those type of robot I just introduced, they are working serial, which means they are kind of type of like a joint after joint. Another type of configuration, we call them parallel robot, which means we have a platform on the top, and we have another platform on the bottom, and we have a number of legs to connect them together. Okay, these are the legs. So the definition of that is the robot with a structure consisting of multiple axes at their tip that move in parallel, and so they are called parallel link robots. So compared with the serial type of robot, parallel robot, normally they are physically constrained in a small workspace. And but at the same time, because if you think about the motion, you use multiple axes to generate one type of motion. So your energy that it can generate are normally more than greater than the what the serial robot can generate. And also you can see the arrow in positioning of this type of robot, they are normally average. If you think about a vertical movement, they actually controlled by these three axes. So the arrow in positioning are average. But for the serial robot, it's going to be cumulative. And if you look at the configuration of parallel, then you can also use the term to describe the type of robot. For example, if we look at the three-leg robot, we can use the symbol PRS to represent prismatic joint, revolute joint, and also spherical joint. For example, we look at the picture A as an example. This is like a platform, one platform on the top, and then one platform at the bottom, and you have three legs to connect them together. So this is a translational joint, prismatic joint. This is another prismatic joint, and this is a spherical joint. So the term for that will be called three PPS parallel mechanism, and the letter P with the bottom line will represent. So this is the joint that can actively be actuated. And with this type of the robot, you have another important thing to consider, which is called workspace. For example, Cartesian robot, you have a workspace like that, cylinder robot, spherical robot, and articulated robot. And some of the commercial robot, you will have a workspace like this. And if you're going to buy a robot and you look at the menu, you will probably see something like this. And this is one important consideration if you're going to buy a robot for some medical application, either for research or for some clinical use. Because you know, for example, some of the robots like a KUKA, they've already got the clinical approval. So if you're going to buy the robot and you are to think whether this robot is going to fit into my application, then you need to look into the workspace. And that will tell you the reachability of the robot, which will answer your question. And another important concept in here is called degree of freedom, which is, again, very fundamental. So we know in the word space, right, if we want to represent the object, we need 6 degrees of freedom, 3 translation about X, along the X, Y, Z, and 3 rotation about X, Y, Z. But how about a robot? If we want to think about that question, we may want to look into our human arm as well. So have you ever given a thought to the numerical value for the level of freedom that you have in your arms? If you look at the left picture, actually we have a degree of freedom that can do the front and back tilt of the shoulder, another degree of freedom for moving the shoulder left and right in here. And then we have the degree of freedom for twisting the upper arm, and then bending and stretching the elbow, and also twisting the forearm. And we have the degree of freedom for bending at the wrist, and also the move the wrist sideways. So we have 7 degrees freedom for our human arm. And for robotic arm, and normally we know that we can have 6 degrees freedom. That will be enough to meet the need to position something in a 3D space. So when a robot compromises a minimum degree of freedom of 6 in a 3D space, basically it has the ability to reach a free position and orientation. So we know 6 is a gold number, but actually there are many robots, they have either less degree freedom or more degree freedom. That end up in two important concepts. One is called under-actuated robot, which means the robot that has fewer than 6 joints, and therefore is limited in the factor poses that it can attain. Another important concept is called redundant manipulator, which means the robot with more than 6 joints, which will apparently give you actual flexibility. So I'm going to give you one example of our research. So this is a research example from our study. This is a dual arm robot for ultrasound, which we have some technique to process two ultrasound imaging at the same time, which will give you a better imaging. But because of that, we need the robot to give a really high accurate positioning, and therefore we build a 2 arm. So for this design, each of the arm has 8 degree freedom. The reason for that is you need some redundancy and also need some flexibility. If you look at the video that I'm going to play in here, you can see when one of the arm come to this side and the other arm also need to move to this side. So the previous arm need to move away to give space for the other arm. So you can see this is a result of flexibility. And if you want to reach this type of flexibility, then probably you need more degree of freedom. So that end up in redundant manipulator. So if you look at the medical robot, I think for the classical serial robot, we'll have 2 important kinematic type. One is called SCARA robot, which means the robot is kind of like the horizontal articulated system. And for this type of robot, the workspace is well fitted for an interventional volume, like what has been shown on the slide. And also in case of fault, it can't collapse on the patient under gravity because of the horizontal articulated nature. Another important category of the classical serial robot is called anthropomorphic manipulator, which means it tries to mimic human arm. So for this type of robot, they are more like a vertical articulated arm if we use the concept we just introduced. And we can see the part of the workspace is actually not used. But it has some of the advantage. For example, it can reach the other side of the patient very easily, and it needs brakes to prevent the robot from collapsing. So I'm now going to give you some example of this type of classical serial arm. For example, the robot duck robot. We have already talked about this robot in the introduction of history. So this is a type of robot that comes from the SCARA robot. It has a revolute joint in horizontal plane, and then it has another 2 degree freedom to orientate the end 2. So this is a orthopedic surgical device which was created for hip and knee replacement surgeries, and it became the first surgical robot to perform procedures in the US in 1992. And also, if you go to the Smithsonian National Museum today, you will also see this robot, right? So this is an example of the SCARA robot, horizontal type of the robot that is used for medical. And for anthropomorphic robot, I'm going to give you 2 examples. One is called CASPA robot. Apparently, it is a vertical orientated robot. And this is also for the bone surgery. Another example is from our research. So this is one of the robots, the picture on the right side of the slides. This is a robot that we developed for ultrasound manipulation. It has 8 degree freedom. And it is an anthropomorphic design, which is to resemble a human arm. So the characteristic of this arm is it is very lightweight, and we have 5 degree freedom embedded into very small areas. It's only about 20 centimeter, and the total weight of these 5 degree freedom is only 2 kilograms, and they are all from 3D printing, which means if there's any failure of the system on control electronics sensor, there will be only 2 kilo on top of the patient body. So this is a design of an anthropomorphic robot arm from our research example. Okay, this is another picture to show our robot, which is a 8 degree freedom robot. You can see the size of the robot is not that big, and this is a phantom for fetus. Yeah, so this is the picture on the right shows our clinical test of this robot. We have already talked about classical serial robot. We also have another category of robot called non-classical serial robot. And this is actually motivated by the laparoscopic surgical procedure. If you look at the picture on the right, so this is a typical configuration for the minimally invasive surgery. And you notice that your movement is actually constrained by the clinical application, because you need to put a hole in here and insert your tool. So your tool can only move in 4-degree freedom, translation, and also 3 rotation. And please note that 3 orientational change are happening at about this point. So they are rotating about this point. And because of this reason, you need some specifically design to meet with the clinical need. For example, you can do a passive arm. One example we already talked about is a ZS robot. So if you look at the configuration of this robot, is a PRR system, and specifically it has 2 joints, which are passive joints, which means that you can manually move around this joint. So you have a prismatic joint in here for translation, rotation joint in here, rotation joint in here, and you have another 2-degree freedom in here, which you can adjust the U and the pitch motion. And finally, you have an active rotation joint to do the roll motion. So this is like a hybrid arm with both active axis and passive axis. Also, sometimes the reason that you use a passive arm is for convenience. So here again is our research example, which is a nasal swab sampling robot we developed this year. So this robot is used to take samples from nasal cavity, and for the pandemic period time, it might become very useful because the clinician doesn't need to be in close contact with our patient. They can control the robot remotely. So the design of the robot was based on a concept of hybrid system. It has 6 passive degree freedom. So you have a passive arm, which you can initially position to let the swab to go into the patient nasal cavity. And you have another 2 active degree freedom for translation and rotation, where the operator can control remotely to acquire the acquisition. So this is an example from our system. And you can also achieve this kind of motion to address the need for the minimally invasive surgery by using a mechanism called remote center of motion, which means the tool can rotate about the point. So if you think about a robotic arm and they're going to rotate about this point, then you need to do a very, very complicated control to move in this kind of trajectory. Many axes need to move together. This is quite challenging, and this is, might be unnecessary. So the alternative way is you use some specific mechanism, for example, the 4-bar parallelogram, which means this type of mechanism can allow you to rotate about this point, which is a remote center of motion. And actually the Da Vinci system, which is the picture on the right, use this configuration. So the tool is always going to rotate about the entrance point. And this mechanism is also used for the eye surgical procedure. You also have an incision in here, and you need to rotate about that point. And this is an ultrasound robot for the carotid artery, and you need to orient the probe about a point, and then you end up in this kind of type of mechanism. And you also have some other type of mechanism to achieve the remote center of motion. So this is a project from Europe, and actually has been took place for many years in France. It's called ultrasound robot, and it has a specific kinematic configuration that you have your rotation joint arranged in a kind of a circular way, and their center of rotation actually intersect at one point. So as a result of that, the system is going to rotate about this point, which is also another way to achieve the remote center of motion. So that was for the serial robot. And for the parallel robot, I think one of the most widely used platform is called steel wall platform, which is a 6-degree freedom platform, a parallel robot. So as we have already introduced, this type of robot, they have a really good payload, but they can work in a very limited workspace. But also, they are very precise, so they can be used for many procedures that require precision, for example, eye or brain surgery. And also another type of robot which are very famous is called continuum robot, which means snake-like robot. This is widely used for intraoperative application. The original inspiration is actually from the marionette. So if you think about the joint link configuration, and you put a joint, you put a link, put a joint, and then you put a link. And you can put a cable to bring them together. And if you pull the cable, and the link actually will move. So this is a basic concept in here. And if you have multiple cable in here, one cable, two cable, then you will be able to actually bundle component, which actually end in this type of continuum robot. So the example of this type of robot is for example, the bronchoscope, which is type of device that can go into your lung and take an imaging, and this is widely used for the lung cancer diagnosis. And because of that, you need to be able to control the tip motion by some of the mechanism remotely at the handle. And actually, the way to make it happen is use the wire mechanism in between. And that end up in this type of continuum robot. There's a video in here, but I'm not going to show that for the time consideration. Another research example is from us, which is a robotic catheter for cardio ablation, which means you can put in the catheter and it can go all through the vascular system to go back into the internal structure of the heart. And it can do some ablation at the tip of the catheter and to remove some of the tissue. And in order to make some of the very accurate control within the patient body, you use the continuum mechanism with different cables. And therefore, you can bend the tip move in this two-direction bending. And again, there's an example from our research. So this is a robotic transit soft-feature ultrasound robot, which is to assist the interventional procedure for the cardio surgery. Again, I have talked about this clinical background in the early slide. Basically, when you do interventional procedure, you can't see the device, so you need to use X-ray, and also you need to use ultrasound to see the tissue. And because of that, your operator is exposed to radiation. And that includes the sonographer who is working here. And we have a consideration that probably we can use a robot to replace the operator in the operating room, what we call them cath lab. And our operator can be in somewhere remotely. They can be in the control room in the adjacent room, or they can be in the centralized hospital, or they can even in their home environment. So the control can be done remotely over internet and 5G or local area network. So we built this robot. And I'm just going to show you some of the motion of this robot as an example for the continuum robot. So this video shows them controlling this robot from joystick. And this is translation axis, and this is a rotation axis. And inside of the endoscopic mechanism, there are cable and wires, so you will be able to control the bending of the probe tip. You can see this is bending left and right, up and down. So this is the example of a continuum robot that we developed. And also we have a soft robot, which has become a very hot topic in recent years. And normally they use the fluidic or pneumatic actuator. And normally they have some kind of elastometric materials or flexible material, for example, silicone, cloth, paper fiber, or some sort of particles. So you know, the use of the soft robotics, especially this type of soft material, actually bring in some intrinsic feature, safety feature of the robot. And again, I'm going to show some of the example. For example, from the Harvard Biodesign Lab, which is a hand rehabilitation and assisted device. And you can see these are the channels to, I guess this is a fluidic actuator, so you put fluid into there because of pressure change, you will be able to actuate this kind of soft material. Another example, again, is from our research, is called the STIFLO project in King's College London, which again is for the keyhole and minimally invasive surgery. But this type of manipulator was made by a very special type of silicone and also flexible materials. So the manipulator can control the stiffness, and it can squeeze through narrow gaps and openings. So it basically increase the safety. And here are some other examples for our research. This is a soft robotic end effector for the robotic ultrasound. Again, you can see some silicon actuators controlled by the fluidic actuation, and that will control the motion of the ultrasound probe, which is in close contact with the patient. And because the use of the soft actuator, this becomes like a really safe working scenario. There's also another very interesting type of robot in recent years, which is called capsule robot, which is like a very small capsule device that can go into your esophagus, stomach, and you can take camera imaging as a replacement of the conventional endoscopic device. And normally you will need to look into, like, for example, the biocompatibility and safety of electronic circuit and machine mechanisms. And also you can use some external source to drive the capsule. For example, the picture on the right. What happening here is that for the capsule, you got a permanent magnet mounted onto the device. And then you have an external robot to hold a magnetic field generator. And that magnetic field generator can drive the capsule, go through your esophagus and all the way into the stomach. So this is like use external source, energy source to drive something internal, and it doesn't need motors to mount it onto the device that go into your body. Okay. So this is a very long section about the configurations of different type of medical robotics, and also showing many examples. So hopefully this bit is will be interesting for you. So now I'm going to talk about the design very quickly. So if you're going to design a robot, what are the things that you need to consider? So the first thing you need to consider is mechanical structure, transmission mechanism, which means that mechanical engineering still play a very important role in the robot design. So here are some examples of our previous robot. I'm just quickly showing you, we have bell mechanism, linear rails, we have gear mechanism. So mechanism, transmission mechanism, mechanical structure, they always be the consideration. So I would say mechanical engineering, they are very important part of the people that we require in the design of medical robotics. And then you need computer-aided design technique to basically make the robot happen. And we know the CAD technique was very important and widely used in many industrial applications. And by the way, this is an example of the very first CAD application. And this is also the founder of the computer vision. For example, this is like a sketch pad. This is called sketch pad. It's like use a light pen to draw on a CRT screen. And when coming to the 1980s, CAD technique is widely used for industrial. For example, the Boeing used CATIA to design their 777 aircraft. And now, today, for example, if you're going to design a medical robot, what is the software that you're going to use? I would say that if you want to start from mechanical level, then you need to use CAD software. And the most widely CAD software at the current days are SolidWorks and Libre. So SolidWorks only works in Windows, where Libre works on Mac system. And alternative to these commercialized software, there are also open source free CAD software like FreeCAD. So if you are a postgraduate student and you want to do some design, you want to make a small robot and you couldn't buy the SolidWorks or Libre, you can use FreeCAD, which is open source software that can run on multiple platforms. And once you have your design, you need to manufacture. I think nowadays, there are two important types of manufacturing process. One is called subtractive manufacturing, for example, CNC machining, which means you have your material and then you do your CNC machining, which is a subtractive manufacturing process, and you end up in your 3D object at lots of waste. Basically, you cut into your material and end up your structure. And also for 3D printing, which is what we call additive manufacture, then you have your material. For example, they can present it as a filament that go into your 3D printer, and you do layer by layer additive manufacturing, and you end up with a 3D object, a small amount of waste. And for 3D printing, you have two important type of devices. One is called FDM, which means you use extruded melted filament and do layer by layer modeling, or the SLA 3D printer, which means you shine a laser at a precise point and basically cure the resin in place. And basically you need a long period of time to finish the 3D printing, but normally it's really quiet compared to the FDM printer. Once you have your design in CAD software and you have your design manufactured, then the next thing you basically want your robot to start to move. And we need to use actuator. So actuator, they are the element in the system that can generate motion from a power source, for example, electrical, pneumatic, hydraulic. So in mechatronic, I think the widely used power source are electrical, and we have motors, for example, DC motors, stepper motor, and servo motors. If you put this motor together with some mechanism, for example, the ball lead screw, then we end up in some linear actuators like the video show on the right. And we also have some other type of actuator from smart material like piezoelectric device, shape memory device, polymer, artificial muscle, and also the soft material. So for majority of medical robot that you can see either for research or it is already a commercial ready product, they use electrical motors. And there are different type of motor, for example, DC motor, stepper motor, servo motor. And if you're going to choose the right motor for application, then you need to consider a number of things. Or if you buy a robot, or if you have a robot come to your hospital, then probably the first question you want to ask from your provider is what type of motors does the robot use? And what is the performance of the motor? Because that will decide your actuation capability. What you need to consider here, a number of things, for example, position control and whether you need the encoder, which can give you position feedback. For example, DC motor, they are a type of open loop device, where stepper motor, they are closed loop. And you also need to look into precision, resolution, speed control, torque characteristics, and also you need to look into driver controller. And also if you have multiple motor, then what is the synchronization problem? So these are the things to consider if you're going to work with a motor. In addition to motor, there are also some very interesting material and also very interesting actuation way that you can make use. For example, the piezoelectric actuator, which has really high stiffness, although it can only move in a very small amount of distance, but it is very, very accurate. For example, in University of Dundee, where I used to study, we had a type of middle ear implant, which we put in some of the device. And then this is a piezoelectric actuator, which can use a piezoelectric effect. You apply voltage and it will end up in the mechanical motion. And that will basically amplify the sound wave, which can help with the hearing loss. We also have an important type of actuator called shape memory alloy, SMA, which can deform into another shape at a lower temperature. And then if we do some reheating above a certain temperature, it can regain its predefined shape. We have already talked about the catheter device, which was the device that I just mentioned that go into the patient body. And we talk about continuum robot, which we can use cable to bend the tip. But also another way that you can bend the tip is to use the SMA material. Then you can bend your tip, you can adjust the orientation. Another example in here is the stent that you put into your vascular system, which is really an important type of material because of its elastic performance. In addition to actuator, in the medical robotics, we also have microcontroller, which is like a small PC, and it has microprocessor, it has RAM, it has memory, and there are many different types of microcontroller. But if you're a postgraduate student and you want to do some robotics, the one that I'm going to recommend you is Arduino, which is very widely used hobby level of microcontroller. But we actually make use of this hobby level controller to design the robot that I just mentioned, like the ultrasound robot. So it's quite powerful. Okay, so this is a little bit about the design of the robot. Just very quickly to give you some very, very basic concept in case of some of our postgraduate students are interested in that, how do we design a medical robot? And then we're going to talk about the force sensing. So why does force sensing so important in medical robot? If we think about a surgical scenario, the most important feedback that you can get for a surgeon, I think there are two types of inputs. One is the visual feedback. If you use robot, you can replay with a camera, you can replay with ultrasound, X-ray imaging, that all provide the visual feedback. Another important category of the feedback is the tactile feedback, which is provided by the force sensor or tactile sensor. So that is a very important aspect of research in medical robotics. So the basic concept of force sensing, basically, I think most force transducer, they measure force indirectly by sensing the deflection. You wouldn't be able to directly measure the force. You can only measure deflection and then convert back to the force, right? So, but at the same time, your force sensor should normally have undetectable deflection so that the normal positioning tasks for the end effector are not affected. And then if you put multiple force sensor into an array, you form like a 2D array of load cell, then you basically have your tactile sensor. And the component that you can use to achieve the force sensing, there are lots of components that you can use actually. For example, the strain gauge, optical sensor, and force sensor resistor, piezo field. For example, this is a torque sensor, and you have your internal shaft mounted onto the previous link, and you have your outer one that connect to the next link. And because of the rotation movement, there will be a small displacement in between that you can detect by your optical sensor in here. So this is an example of a torque sensor, and you can also use the strain gauge to form a conventional force sensor. So strain gauge is type of device. It's like resistors, but the resistance will change based on the level of deflection. So the picture on the most right shows a configuration of a force sensor used in a robotic joint. So you have your robot, and you put an adapter in here, and you put your force sensor, and this is a tool that you are going to mount it at the distal tip of the robot. So basically, you put your sensor between the joint and your tool, and you'll be able to measure the force at the tip. So here are some examples of commercialized force sensor, and we also have some example from our research. So this is a customized sensor we developed for our ultrasound robot. You can see this is like a two-piece design. Then that's the reason why do we need a customized design that we need to put in the ultrasound probe. The bottom one shows example of the force sensor that we designed for continuum robot. For each of the link, we put some optical sensing element, and that becomes like a sensor, and that can sense the force, which will also help us to decide the shape of the continuum robot. This is about the sensing of medical robotics. And then we're going to talk a little bit about the control of medical robotics. So when it comes to control, I think there is some important concepts and some important of the principle that I'm going to introduce you. So for example, kinematics, which is a very important thing for medical robots, which means how do you control your robot to reach a certain task? It basically, a certain position, it basically answered that question. And normally for kinematics, we will have two types of kinematic problem. One is called forward kinematics, which means that you know each joint angle, for example, how many degrees does the first axis rotate, how many degrees does the second axis rotate, and eventually you want to predict the position and orientation of the tip in 3D space. So this is called forward kinematics, forward approach, and that can be done by some conventional method, for example, the DH method. Another type of research problem fall into inverse kinematics. For example, if you know the position and orientation of your end effector at the end, how do you configure your robot in order to reach that position orientation? So this is called inverse kinematics. And normally you can do it with a closed form mathematical solution, or you can use numerical method to solve the problem. And when we solve the problem of kinematics, we come to the next level, which is to talk about the human-robot interaction. This becomes very important for medical robotics because medical robot, different to industrial robot, they're going to work with patient. So basically, you can think about medical robot working in three different scenarios. The first one is coexist, that the operator do something and the robot do something else. For example, the small autonomous cars in the hospital to transport some of the samples. This is like a coexisting scenario. The second scenario is called cooperation, which means typically, for example, the master-slave configuration we just introduced, that the operator does something and the robot try to follow exactly what the operator does. And the third configuration is called collaboration, which means that actually the robot is in very close contact with the operator. That operator, we'll think them as the surgeon, because apparently the robot is going to in contact with the patient for most of the scenario. And in that case, for example, the assistive robot for rehabilitation, you see the robot basically work together with the patient. And for an ultrasound robot, you can see that the operators actually control the robot and in close contact with the patient. So this is like a collaboration, and you have much more things to consider. For example, the robot is going to in contact with the human, right? And there will require some level of safety control. And I'm going to give you some further example of that. For example, the Da Vinci surgical system master-slave configuration, surgeon working in the console and the robot in close contact with the patient. So this is like a master-slave operation, and this is a kind of, we'll see collaboration. And also the MC2E robot, which is a type of robot also used for the keyhole surgery. And you see the surgeon actually control the robot. The surgeon hold the robot by themselves, and the robot will do some other operation. So this is like a surgeon-robot cooperation. So you can see the medical robot, they become very complicated. You have lots of different combination between either the robot working close contact with the patient or with the surgeon or with both of them together. Then you need some of the control, right? The basic control will be the force position control. And we have different level of control. For example, position control, that you don't consider force at all. For example, you move the robot in a linear path in a constant speed, and you don't care about the force at all, which will result in some of the damage to the end tool, and also it can cause safety concern for the patient. And again, if you improve this type of control to the force control, which means in order to reach a certain level of force in close contact with the patient, then you need to do an adaptive path, which becomes really complicated. You need to follow the path. You need to sense the force, and you need to use the force as a feedback to follow the path. And but still, you can use constant speed, right? Then you have your controlled contact force. And also, if you do further improvement, then you can control the speed as well. Then you have your pass, right? You can do either fixed pass or you can do adaptive pass, and you can also control your speed. Your speed can also vary. So basically, you can see there are a number of things to consider for control. One is position, whether you can reach a position, and then what is the trajectory that is going to follow. And during the trajectory, whether you're going to consider the force and whether you're going to consider the speed. And then it comes to a very important concept in medical robotics called compliance, right? So what is compliance? We'll give you an example of the compliant end effector. So it can reach several positions and exert different forces on a given object. For example, a compliant robot gripper can grasp an egg without crushing it with the proper settings. Or we say a compliant robot arm can automatically retract where the patient is pushing the arm. So if you think about the scenario, for example, an ultrasound robot is taking ultrasound imaging of a patient, and suddenly the patient stand up. And what's going to happen with the compliant robot, that the robot is going to automatically retract. So that is the result of compliance. And actually, there will be two different methods that you can result in compliance. One is active compliance, which means you can use programming, you can use algorithm to make that happen, and which means you also need sensors. So you have vision sensor, you have force sensor, you have torque sensor, which can sense the word, sense the movement of the patient, and then you can feed them back to the robot control loop, and the robot can retract, robot can adjust orientation, robot can adjust the force that it can exert. Another type of the compliance can be achieved by the passive device. And normally they are inherent to the structure of the robot. For example, a torque limiter device, which can limit the amount of torque that a joint can generate. And what is a good design of medical robot? I think they will have two different levels of compliance. So if you think about a collision scenario, then it will first be controlled by active compliance. You detect the faults, your torque fault sensor tells you actually there are too much faults. And then you basically, you retract your end effector or you do some kind of a motion adjustment. And if that fails, for example, you suddenly have an electronic loose in your hospital, the robot stops working, and then you lose your active compliance completely. And then your passive compliance is going to take over. For example, you have some of the mechanical device, like a torque limiter, that when they come to a certain threshold, it's going to automatically disengage, that the robot will no longer work. It can't generate much force than the threshold. And basically, although you can't control the robot nicely, but you can reduce the safety concern. So this is a very good strategy that you have two levels of safety. Start with active compliance based on algorithm, programming, and sensors, and then you come to passive compliance, which are based on the mechanical device. Okay, so for our postgraduate student, if you're going to do some control study, if you're going to do some kinematic dynamic study of a medical robot, then what is the software that I'm going to recommend you? I'm going to choose three examples that I personally used a lot in the last few years. The first one is called CopyDSA, which it just changed name in last year. Previously, it's called VRAP. So the bottom screenshot shows the configuration of the software. So this is actually the robot called UR5 that I built a model in here to represent the ultrasound scan. So by using the software, you can automatically do some kinematic dynamic study, and you can also analyze how far is the robot away from the patient. You can simulate the motion, and you can do quite a lot. So this is a KUKA robot arm used in this scenario. So this is for robotic simulation, also control study. And if you're going to control a robot, I'm going to recommend you ROSE, robotic operating system, which has so many different packages inside of that, which can do hardware control. It can do message passing between different sensors. So it's quite powerful tool if you're going to control a robot. And if you want to do some research study, probably if you are very familiar with MATLAB, then you can use the robotic toolbox from Peter Koch, which is a very famous robotic toolbox. You can see the release 10, right? Just like so many generations. So within a couple of lines, you will be able to generate a medical robot model, and you can simulate your motion in here. Okay, now I'm coming to maybe the last section of my presentation, which is about the pre-planning and navigation. Actually, we also had the safety, that will be the last section. Okay, so we already talked about a lot about the surgical robot and especially the robot for master-slave configuration, tiny manipulator. But if you look at this type of robot, they're actually still controlled by our surgeon. So basically, the surgeon will decide how the robot behave, and the robot will do the task. So this is called master-slave. But if you think about the robot, of course, we will think about some sort of thing towards autonomous, and how do we actually achieve autonomous? And I think important tool in here is the image-guided robot, what we call in here true robot, which means that the robot can do some pre-planning before the surgery, working together with our surgeon together. And then they will decide where the robot should go, what should be the trajectory, and what amount of force the robot should generate. And basically then you press a button, and then robot go and finish the task. So that is based on imaging, pre-planning, and navigation. So basically this is a combination of a robot and imaging computing, which end up in a very important community. And many of you may know this quite well, the MIMTT community, Medical Imaging Computing, Computer Assisted Intervention Society. So if you want to do some pre-planning navigation and apply them to robots, then you need to do lots of medical imaging analysis. For example, you need to look into your pre-scanning data, like MR data, CT data. And in order to do some pre-planning, probably you need to do some segmentation, you need to do some reconstruction from 2D to 3D. And then during the procedure, we will look into the real-time guidance from X-ray and ultrasound. Probably we also have navigation. And when it comes to navigation, probably we need multimodality registration. We also can use the technique from AR and VR to assist the navigation. These sort of things can all work together with a robot to deliver the procedure. And then more advanced, we will have image-guided robot control. For example, the visual serving, which means you use the medical imaging output as the input for your robot control. You analyze the imaging and you let the robot decide what to do, and also the AI-based imaging analysis. So I'm going to give you some example from our study just very quickly. For example, for the registration and navigation, this is one of our research to register X-ray imaging with 3D ultrasound imaging used for interventional procedure navigation. And by doing that, you basically present two types of imaging modality altogether to your surgeon, and they don't need to imagine because they are already well aligned. So this is one example. Another example in here is called a robotic transthoracic ultrasound robot, which is an ultrasound robot. But this robot is used not for diagnosis purpose, but used for guided surgical procedure. And you can use the robot and also some tracking device. And then eventually you can align the X-ray imaging with the echo ultrasound imaging together to guide the robot to do some operation. And if you want to develop something by yourself, and you want to work with a robot, I'm going to recommend two software that I have been using for many years. One is the ITK Snipe, which is a software that you can do some of the segmentation and the 3D reconstruction. And another one is called 3D Slicer, which I have been used for many years as well. I used them to develop the robotic navigation system, which is like an open source software. It has many very powerful toolbox, and also it has the link to some other softwares. As an example, I'm going to show you one of the work from our research. Navigation system for the transesophageal ultrasound robot. Remember the robot that I've introduced in the early time of today's tutorial. We have developed a robot which can go into patient esophagus and take ultrasound imaging of the patient. And I used Unity to develop a navigation platform which you can predefine where the robot should go. You can see the heart structure, you can see the right line is the central line of the esophagus. And it can automatically decide where the probe should be placed in order to get a certain view. And that will basically tell the surgeon where to go. And also that can be remembered by the robot, and the robot can actually try to go to that location. And then in order for the robot to go to that location, you need some real-time guidance. And that comes to very important tracking devices. One is, and I'm going to give you two examples. One is the electromagnetic tracking, and very importantly, it is a very famous device from NDI, which is EM tracker. Basically, you put the tracker at the end of your tool, and you have your field generator, which can generate a magnetic field, and that will tell you where your tool is positioned, oriented in 3D space. And also you can do optical tracking, which you can use the stereoscopic sensor, and you put your LED onto your surgical tool, and you will be able to sense the position, orientation of your tool. And you can think about the application, right? For example, for the optical tracking, it's not going to work if you're going to do some intraoperative surgical procedure, or if your robot is going to go to the inside of the patient body, because the light is not going to be detected by the sensor. Then in that case, you need to use your electromagnetic sensor, but this type of device is going to be influenced by the magnetic field. For example, if you have multiple motors running at the same time, which apparently is going to generate the electromagnetic interface to your sensor, and that will end up in a kind of error in your position orientation detection. Okay, now finally, I'll come to the last section of my tutorial about safety. I'm trying to finish in 5 minutes. So, okay. Safety is very important for medical robotics because we need to consider quite a lot. The robot is going to cooperate with humans, surgeon, staff, patient, and interact with the patient as well. And we know that the component of the system, if they are in close contact with the patient during the surgical procedure, they probably need to do the stereo and they need to be sterilized, right? And we also know that in the operating room, there are always many other medical systems, like for example, in a surgical operating room, you will have a surgical bed, right? You will have your X-ray machine, say arm, and you probably have lots of other devices at the same time. So a robot is not going to be, go into this device, collide with this device, which is the last thing that you want to say, actually. And also you need to know that surgeon is not robotic specialist. So you need to develop some of the user-friendly human-machine interaction method and also how to do the maintenance. So these are lots of considerations that you need to think about if you want to have your robot to be translated into the practical use. And also we need the robot to be easily and quickly transported out of the operating room. So if you look at the regulation and rules, I'm not a regulatory person, but in general, if you look at the European community, you have ISO 9000, you have your CE marking regulation. And in China, there are also similar kind of regulation, although they'll be slightly different, but normally they will be classified into different classes, class 1 device, class 2 device, class 3 device. Although the regulatories are different, but there are some common considerations. For example, the lifespan use, whether this is a temporary device or is going to be used for several years, like an implant. Whether this is an invasive device or non-invasive device, whether this is used for surgical or non-surgical use, or whether this is an active or inactive. Remember, we talk about the active arm and passive arm, the responsible, who is going to be responsible for that will be different. For active system, the robot is going to take in charge. For the passive, the person who's going to take in charge is the operator. And also, we know that we need to look into the vital or non-vital body part, concerned by the device. And then eventually you end up in several, TY things that need to consider: safety, reliability, availability, confidentiality, integrity, and the maintainability, right? And what is the strategy to make your robot safe? I think in general, two strategies. The first one is to make use redundant component, the degree of redundant in control of sensing. For example, the robot we developed for ultrasound scanning, at the end of the device, we will use force sensor. We will also use proximity sensor, and actually we have a kinetic camera that take the 3D structure before the procedure. So there are actually three sensors to guarantee the safety. And there will be some kind of a bypass control loop that you intentionally design to address the safety concern, to think about if that part of circuit stop working, what's going to trigger whatever. Okay, the second strategy is to design some intrinsic safety feature. Remember the passive compliance example we just mentioned. So I'm just going to give you one example of our research, which is a torque limiting mechanism for a medical joint. So if you look at the joint here, we have link 1, link 2, and here is a joint 2. And this is not a classical joint. It's actually made by spring and ball. So if there are too much force generated at the end, what's going to happen is the ball is going to come out from the detent hole. The ball is going to come out of that, and then you will no longer be able to transmit the motion from link 1 to link 2. Okay, you don't need to understand detail of that anyway, but it just gives you a concept that you can design some sort of mechanism which basically stop the transmission of the force when it comes to a certain threshold. For example, I decide when coming to 20 Newton, the robot is going to disengage. That will always guarantee the safety. So this is a strategy for safety. And I'm going to tell you about two very useful tools that you can use for analysis. For example, after you build your robot, how do you evaluate the risk? And especially, you know, if you want to get the robot commercialized, the first step is you need to do the clinical trial. And in order to do clinical trial, what you need to do is you need to apply in the hospital. And then you need to submit your ethical application in order for approval. And then you need to submit something, right? And then what is the thing that you need to submit? Probably this can be one of the tools that you can use. For example, the hazard traceability and risk evaluation matrix, which includes 3 different components: risk analysis, risk evaluation, and risk control. So I'm giving you one example, right? So risk analysis, the hazard that I identify in my system is the vertical mechanical force on the patient. And then you will analyze what is the foreseeable sequence of combination of the event that can trigger that, and what is the hazardous situation, what is the harm, the possibility, the severity, and then you can check the table, you found the acceptable, whether this is acceptable. And then you go to risk control. What is your risk control option, and what is the measure, and how this risk control is verified? For example, this is one of our study example. You can see the risk control verification. We put some citation to our other documents and other research paper. So for example, sensing test report, right, done by who and whom, and this is the one to verify that the risk control. So the risk control is actually valid, effective, and the status is closed. So which means this is already solved. And then you reanalyze the possibility, severity, and the residual risk, and you end up in a residual risk. You can see this is yellow, and it has been increased to green after you put in your risk control. Okay, this is also in the other slide. Anyway, it doesn't matter, it's the last slide. So another tool is called FMECA and PFMECA. So this is another tool that you can use. So the previous one is basically you do from up to bottom. You identify a hazard and you analyze what can trigger that hazard. And for this one, you basically look into something small from bottom up. For example, if a motor stop work, what's going to happen to the system, and then the potential cause, and then proposed control. So basically the previous one is from up to bottom, right? For example, if I look into the false, and then I know there are a number of reasons that can trigger. And then the next one, you start from something small, and then you go all the way to the up. Okay, so now coming to the end of my presentation, and I'm going to give a very brief summary. What's going to be the future of medical robotics and where we are at the moment? So this is a very famous picture from many of the the top scientists in medical robotics. So this is published in the Science Robotics. They mention different level of autonomous that the medical robots may have. So start from no autonomy, and then robot assistance, which means the operators maintains continuous control of the system where the robot provides certain assistance. And then you go to task autonomous, which means that operator will maintain discrete control of the system, and the robot can perform certain operator automatically by itself. For example, some of the imaging guided procedure, the robot automatically go to some target position in a certain period of time during the procedure, right? So this is a task autonomy. And then you go to conditional autonomy, which means your operator can select the surgical plans, and then the robot will basically perform the procedure automatically, but with the close surgical oversight by human. So you can see the difference between the task autonomous and conditional autonomous. For the task autonomous, you just do one task. For example, move the robot from one place to another place. So this is done automatically. But for the conditional autonomous, many of the things are done by the robots automatically, but this is under the close guidance, close oversight by human. And it is the human to select the surgical plan, not the robot to select the surgical plan. Remember, this is very important here. And then you go to high autonomy, which means the robot is able to make decision. You see here, it's not the surgeon make decision, but the robot make decision, right? but this is again supervised by the codified operator. And this codified operator, it might not be necessarily need to be the surgeon, right? Please be careful about the use of the word codified operator. And then we go to full automation, which means, apparently no human, right, in here. So where we are at the moment, I think we are still in the robot assistant and the task autonomy level. How far are we from reaching to higher autonomous, and what is going to be the consequence of autonomous is a very interesting questions. And I think we have a very good presentation section in the following days, and probably you guys will find out some of these from those presentations. So thank you. This is all about my presentation. Again, I would like to thank for the invitation from the conference committee. Thank you so much.
Thank you so much for an amazing presentation. If I was younger, I would certainly pick up on robotics for my next area of training.
Thank you, thank you.
Very inspiring. I don't know if we have any questions from the attendees. Maybe they can ask their questions in the Q&A box. And with that, I defer to my co-chair, to Yang.
I already see the question asked in Chinese. So the question is about if you have a medical robotics in the past planning process during the surgical procedure, what are the kind of evaluation metrics that can use? And the second question is how do you evaluate the safety? I think these are really good questions. So for the first question, for the past planning and for the evaluation metrics, I think there will be some important, very important metrics. Let me give you some example. For example, what are the distance of your device away from the patient? If you go to the medical device regulatory, you will see some of the device, if you want to pass like class 2 or class 3, that during the operation, you need a certain distance away from the patient, and that could be one of the metrics. And also, you can see the smoothness of the trajectory and the amount of force that you can exert, like what I mentioned, whether this is a force control or whether it is a hybrid control, both force and the position, that you can apply certain force and also reach the position at the same time. This could be another metrics. And also, I think apparently it's the accuracy, right? If you pre-plan that surgical pass and how accurate the robot can achieve that, and also is I think it's the reaction to the patient motion. For example, in many cases, the patient may brace, right? And also, in some of the, if it is not fully under anesthesia situation, then probably they can move. And what's going to happen if the robot move? Do you have feedback to adjust the pass, or is the pass is always being a fixed pass? And if the patient move, then it will result in somewhere else. And the second question is how to evaluate the safety. How to evaluate the safety? I think two different level. The first level is like at the end of my presentation, and introduce some of the tool that you can use. And basically, you need to list all these kind of foreseeable sequence if something fails. And then you need to look into the method to resolve that. And you need to perform lots of repeatability testing, repeating tests in order to give you the evidence to say, okay, I do have this measure and which can address the safety concern. So this is from kind of application level that you do lots of that. And then from the practical level, I think the safety need to be really verified when the robot goes into a clinical scenario, because as I mentioned, our clinicians, they are not robot expertise. So sometimes even if you make your robot safe, probably the collaboration between the robot and the surgeon may end up into some other problem. So yeah, so this is a short answer, but I'm happy to discuss more later on offline. Thank you.
Thank you very, very much for your presentation.
Thank you, Kansari.
So if there are no more, let's say, yeah.
I'm sorry, I'm here. Actually, I am muted. Yeah, Shuangyi made a very good talk about the medical robotics. His talk crossed almost all the aspects of the robotic designs and applications and all the required technologies. It's great. For my question, I can ask Shuangyi a question. You know, there are in whole robotic design, there are many optimizations. And the path optimization, the freedom optimization, and some guidance like image or some sensor signal also optimization. So when you consider this, how to use prioritize these optimizations to make your robotic system achieve your accuracy and safety?
Okay, thank you. Thanks for the question, Professor Yang. So I think first we need to identify whether the robot is used for surgical procedure or whether it is used only for guidance. For example, if I have a surgical robot, then apparently the precision will be one of the priority that we need to consider. But if the robot is not used for surgical directly, for example, the robot that I developed, which is an ultrasound robot, then precision is not one of the important things that I need to worry about, because it doesn't really matter if I have like a half centimeter arrow. Then in that case, something else will become my priority. For example, the workspace, whether it will fit into my application. So I think first of all, we need to decide from the task and then decide what is the priority for your specific application. And then we need to do lots of optimization like you mentioned. And that I think before the design of a robot, we need to do lots of simulation. So previously we will build a model in the CAD software, and then we'll do some like video simulation, and then we'll show them to clinicians, which is very important. We'll show them this virtual environment and they will provide some feedback like, oh, actually, this is not the good way to arrange a robot. It should be in the right side of the patient rather than left side. And it looks very scary, then you need to adjust that. And the interesting of that is you might find something that out of your expectation. So for example, sometimes you think actually a robot with a good cover will actually be more attractive. But in our survey for like hundreds of doctors, they turn to choose another design actually, which looks more industrial. So this is for the feedback from the clinician, and then it's the feedback from the patient. So what we also do previously is we will show some video simulation of how the robot is going to work, especially different versions we design to the patient. But it's also need ethical approval actually. So we'll show these sort of things to them and let them to rate which one is the best design. And then we will basically put that back into our design loop. So I think, and to be honest, first need to decide what is our priority in that specific application. And sometimes, you know, people like to buy a robotic arm. For example, you buy a KUKA arm and then you use for some application. But probably your application doesn't require that accuracy, that amount of force at all. Then probably this is not the right robot that you need to buy, okay, or you need to design. Then the second is to get the patient and the doctors into your design loop, which will help you a lot. So this is my answer. Thank you.
That's a great, very good, very nice answer. Thank you. And actually, I have many questions I want to discuss with you, but maybe time is short. We can discuss later. I appreciate your great talk. It's the content, everything is well prepared, very nice class.
Thank you.
Lecture, yeah, great.
Thank you, Professor.
Okay. Maybe for the audience who still want to listen more about Professor Shuangyi's work, you can go on the October 2nd. That is the Thursday of next week. In the evening session, he will give another talk. You can join in. Now, Catherine, maybe it's I give back to you. You can.
Yeah. All right. Thank you, everyone, for attending, and have a nice rest of the day. Bye-bye.
Bye. Thank you.